Today, I want to go over this problem where we consider a function. I want to talk about how we can determine the function is a linear function and then do our linear function things that we want to do. So let's look at this example. Consider the function capital F at x, values for which are given below. So we're given a table of values. Negative 427, 0, 24, 421, 8, 18, 12, 15. And the first question would be, how do we know that we're looking at a linear function? What we see is a pattern of repeated addition. So from 27 to 24 is a decrease of 3, from 24 to 21 is a decrease of 3, and so on. We're always subtracting 3. The way we can say this in a nice, concise manner is that we can say that capital F of x has a constant rate of change. So capital F at x has a constant rate of change. That's what makes a linear function linear, the constant rate of change, that pattern of repeated addition. To be specific, we would say that f of x decreases by 3 every 4 units. So we can clarify what we mean by saying we can be specific by saying f of x decreases by 3 every 4 units. We could also combine this information by saying f of x has a slope of negative 3/4. And we can write it as a fraction. We could say decreasing by 3 every 4 units. So negative 3/4 will be the slope. But the primary thing we want to say is that f of x has a constant rate of change. We want to identify that there is a constant rate of change. Now we want to do our linear function things. We want to be able to describe our linear function. So it could be that we want to write a sentence describing f of x. Now that we've identified f of x as a linear function, it could be that we want to write a sentence describing capital F of x. And we're going to use the form that we learned to describe linear functions. We would say where the function starts. We could pick any one of these values as a starting point, but we choose x equals 0 as our favorite. So a sentence describing f of x would say that capital F of 0 is equal to 24. So give your reader a place to start, and then describe what's going on. Say f of x is decreasing by 3 every 4 units. There's a sentence describing capital F. We're saying where it starts, where the function starts. We're saying how the function is changing. And we're saying how often the function makes that change. So 24 is the starting y, 0 is the starting x, which we put in quotes because the function goes on forever in both directions. But we got to pick somewhere to start. Decreasing by 3 is a description of how things are changing. In a linear function, since we can use slope, we can call this the rise. And how often the rise happens is the run. We wouldn't want to use those terms in writing a sentence about what's going on. We would just want to describe say f of 0 is 24 and f of x is decreasing by 3 every 4 units. Now that we have a sentence describing what's going on, we need something more workable to do some algebra on. So now we want to write an equation describing f of x. So to write an equation, we say f of x. We start off by saying f of x. We want to describe f of x. And we're going to say f of x equals. Now we're making an equation that describes f of x. I always like to start off with where I started off with in the sentence. I would like to say f of x is equal to 24. And then I want to say what's happening in one number. I want to take the rise over the run. So I'm now going to put the slope of -3. So f of x is 24, and then decreases by 3 every 4 units. To combine that into the slope a bunch of times. So we say then times x. Oh, that should have been 2. Oh well. So here's an equation describing f of x. It starts off at 24 and decreases by 3/4 every 1 unit, which we can interpret as decreasing by 3 every 4 units. So the common thing to do is use the slope, which is the rise over the run. In this case, the rise is a -3, and the run is 4. So here is an equation describing capital F of x. Once we have an equation describing our function, there are a couple of things that we can do with the equation. I could give you an x and ask you to find, give you an input and ask you to find the output, or I can give you an output and ask you to find the input. That is, in the table, I can give you something from the top and ask you to find the corresponding number on the bottom, or I can give you a number on the bottom and ask you to find the corresponding number on the top. That's just the input-output game. So I might ask you to say, evaluate the function at a point. I could say, find capital F at 10. And then usually with this, I would say something like, show your calculations. And maybe round your answer to the nearest 10th or 100th or something. But let's just start with this. So to find f of 10, we're going to take 10 and replace the x with a 10. Because in the parentheses is what we're plugging in. So f of 10 is going to be 24 minus 3/4 of 10. And then we just have to simplify that. Notice that instead of writing x, I'm writing 10, because we're plugging in the 10 for the x. Now we just need to simplify using the order of operations. We have subtraction and we've got multiplication, and the order of operations says multiplication before addition. So this is going to be 24 minus 3/4 of 10, which is 7.5. And then we just need to do 24 minus 7.5. So 24 minus 7 will be at 17. We'll subtract 4 and then to get to 20, and then 3 more to get to 17. And then we'll take 17 and subtract 0.5 to end up at 16.5. Or 16 and a half. Since you're using a calculator, you might just drop it into your calculating machine. 24 minus 3/4 of 10. 16 and a half. The other game that we can play once we have the equation, the other input-output game we can play is I can give you an output and ask you to find an input. So for example, I might say something like solve f of x equals 10. So here we're looking for the x, and then I'll say show your calculations. And maybe round your answer to the nearest 10th or 100th or some such. So here, we're just going to be solving an equation. So I'm going to take f of x. I'm going to write the equation that I have for f of x. F of x is 24 minus 3/4 of x. I'm going to set this equal to 10. Now the 10 is appearing on the other side. We're trying to figure out what x will have an output of 10. So here 10 is the output. In problem 4, 10 was the input. So if 24 minus 3/4 of x is equal to 10, if we just think about what happened to the x and undo those things, do inverse operations in reverse order. So we'll subtract 24 from both sides. That'll be negative 3/4 x is equal to 10 minus 24, which is negative 14. And then I'll divide by negative 3/4. Which is multiply by the reciprocal. So we need to calculate 14 times 4/3. It's going to be positive because a negative times a negative is a positive. And if I do 14 times 4/3, we get 18.67. So 18.7 if I say round to the nearest 10th, or if you want the fraction, 56/3 or 18.67 is 2/3. I forgot the calculator is always going to drop the improper fraction on you. But we want to recognize 0.6 repeating as 2/3. If we go back to our original, or actually before we do that, notice that if we think about what happened to the x here, we can make a plan based on inverse operations in reverse order. We're trying to figure out what x will turn into a 10 through this process. And first, we multiply by negative 3/4. And second, we add 24. So the inverse operations to turn 10 back into an x. First, we'll subtract 24, and second, we'll divide by a negative 3/4. We should go back and make sure this all fits with our original function. So originally we had values for x and f of x, negative 4 and 27, then 0, 24, and then 4, 21, and then 8, 18. The one that we found in problem 4 was that when x is 10, f of 10 is 16.5. So that's the one that we found in problem 4. When x is 10, f of 10 is 16 and 1/2. Then we had 12 and we subtracted 3 again, 12, 15. And then we had this point when x is 18 and 2/3. Oh, I guess we had 16 and 12. We just keep following the pattern. Then we get to the point that where we have 18 and 2/3, 10, and that's from problem 5. So it's like we're going for points that are in between the ones that are 4x apart, 4 units apart in the x. Because if we continue the pattern, the overall pattern, when x is 20, then we'll subtract 3 again and be at 9. So we can see that 18 and 2/3 between 16 and 20 gives us a 10, which is between 12 and 9. And the 16 and 1/2 is between 18 and 15. And the 10 is between the 8 and the 12. Okay, tomorrow what we want to do is a similar problem, but with an exponential function, and see how our explanation changes, how our equation changes, and how our calculations change. All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.